Alright, so let's ask this question. How many necklaces are there with 2 black beads, 2 red beads, and 2 blue beads? To solve this, I'm actually going to ask the more general question that will help you with your homework. Suppose you have k different colors of beads, and that you have ai beads of color I. So that there are n beads in total, where n is the sum. So the case we're working with up above here, k is 3, there's 3 colors. A1, A2, and A3 are all equal to 2. And n is 2 plus 2 plus 2, it's 6. But in general, for any k positive integers, a1 through ak, you can ask the same question. Well, to that end, we're going to try to answer this problem using group actions. So we're going to let n be the set of what we're going to call not quite necklaces. So here, orientation is going to matter. So this is the case where now we decide that if you rotate, you actually do get a distinctly different necklace. Or if you flip, you actually get distinct necklaces. And so if you've labeled the locations clockwise from 0 to n minus 1, what you're really looking at is a function that tells you what the color of the ith bead is. And of course, in general, instead of using k colors, we're going to name the colors as numbers. So the point is, you basically are working with functions here. So you can encode a necklace as a function. And the property we have is that the ith color is used ai times. There are ai beads with that color. So under this function, the ith color has to be used that many times. And so this is the set we're working with. So this is the setup. And why do we care about this setup? Because the dihedral group acts on this set as follows. The rotations act on one of these functions as follows. I take this new function, I apply it to j. What I'm going to get is the same thing as if I applied the original function to j plus I, modulo n. So in a moment I'll explain what this is doing, but right now here's the formula. Similarly, for a reflection, here I'm writing the s on the right, by the way, because it makes the formula a little easier. The reflection, when I take the reflection and I act on one of these colors, these functions, I apply it to j, I'm going to negate j, add I to it, and then apply sigma to that. Here it's worth pointing out I'm working modulo n. And so it turns out the number of necklaces is actually the number of orbits for this action. So we need to show that this is an action. Alright, so let's take this hexagon. Let's look at this particular choice of beads. The corresponding function is this one. So here red is the number 2, blue is the number 3, 0 and 3 both got black beads, so they're both sent to 1. 1 and 4 got red beads, so they're both sent to 2, and 2 and 5 both got blue beads, so they're both sent to 3. Now what is r dot sigma of I? It's sigma of I plus 1. So that means we're going to look at sigma, so r dot sigma of 0 then is sigma of 1, which is 2. R dot sigma of 1 is sigma of 2, which is 3. And then you can see how this pattern works. The idea is each of these numbers is going to move exactly one to the left. So then 1, 2, 3. Finally, r dot sigma of 5 is sigma of 6, which is sigma of 0, which is 1. So in terms of necklaces, what is this? Well, what do you get? 0 and 3 both got red beads. 1 and 4 both got blue beads. And 2 and 5 both got black beads. So I took this necklace and I rotated it counterclockwise. So now we look at this other calculation. Notice that sigma of 6 minus 0 is sigma of 0. So S dot sigma of 0 is just sigma of 0, which is 1. The same thing's going to happen at S dot sigma of 3. Sigma of 6 minus 3, which is still 3, sigma of 3. Sigma of 3 was 1, so those two stay the same. S dot sigma of 1 is sigma of 5. So that becomes a blue 3. S dot sigma of 2 is sigma of 4. So it becomes a red 2. Likewise, S dot sigma of 4 is sigma of 2, which was a 3. S dot sigma of 5 is sigma of 1, which is a red 2. So what did I really do? I just took the top necklace and I took the horizontal reflection going through 0 and I applied it. And so remember, the whole point is that these three necklaces are considered the same. Oh, and that means that these three functions are the same. And so in particular, we should have sigma is equal to g dot sigma for any group element, which means our definition of necklaces corresponds to the equivalence classes of this equivalence relation we get from this group action, which means that we're just counting the number of orbits of the group action, and that will tell us the number of necklaces. Of course, I still need to prove that this actually gives a group action, so we'll do that next. Or more accurately, I'll only do one part. So these were the definitions of how r dot I acts on sigma. So I only did the what happens when you act by rk and r to the I. When you apply this new function to j, you can see that you get j plus k, parentheses plus I, as the argument you input to sigma. But addition's associative, so that's the same thing as sigma of j plus parentheses k plus I. Up to commutativity, that's what happens when you apply r to the I plus k to sigma of j. In other words, if you rotate the necklace by k times and then I times, you get the same result as if you rotated I plus k times. And of course, there are 3 other cases involving reflections, but I think that's going to make the video way too long. If I do that, it's a very similar proof to the proof I had before of the dihedral group acting on the integers 0 through n minus 1. Alright, so we're not dealing with D16 anymore, we're dealing with D8. D12. We're acting on the hexagon. Well, by Burnside's lemma, the number of orbits is given by 1 over the group times the summation over every element of the group, the number of fixed points of that group element. So that means we're going to have to look at the number of fixed points for every group element in order to solve this problem. So first group element we look at, the identity. The identity always fixes every element because one of the axioms for a group action is that E dot x is equal to x. So you get the whole set. And how many such necklaces are there, or not quite necklaces are there? Well, you have to choose 2 of the 6 beads to be black, and then 4 of the remaining beads to be blue, and the remaining 2 slots have to be red. So that becomes 15 times 6, or 90. So next, let's look at the rotation. So what do we mean by fixed points? We're looking at those near necklaces such that when you act by R, you get sigma. Well, what is R of sigma? R of sigma of I is sigma of I plus 1. So this means that sigma of I plus 1 has to be equal to sigma of I for all I. Oh, okay, I should be a little more accurate. There should be I minus 1, right? Because R dot sigma of I. Oh no, I had it right. So if you want R dot sigma of I to be equal to sigma of I, it must follow that sigma of I plus 1 is equal to sigma of I. So if these two functions are equal, this equality must also be true. What does this mean? It means that whatever color you have on the 0th bead, so sigma of 0 has to be equal to sigma of 1, which has to be equal to sigma of 2, sigma of 3, dot, dot, dot. Oh look, you have to require all the beads to have the same color, because you're looking at necklaces such that when you rotate clockwise, you get the exact same necklace. That's not possible with the way our colors work. The only way to have that happen is if we had 6 beads of the same color. So we see that this answer is actually 0. It also turns out that the same thing should happen for the counterclockwise turn, which would be r to the 5th. So if r is clockwise one direction, r inverse, or r to the 5th is counterclockwise the other direction. So now we look at r squared. So this would be, the fixed points here would be r squared dot sigma equals sigma. R squared dot sigma of I is sigma of I plus 2. So we're requiring sigma of I to be equal to sigma of I plus 2. So in other words, we want sigma of 0 to be equal to sigma of 2 to be equal to sigma of 4. And the same thing for the odd numbers. Sigma 1 equals sigma 3 equals sigma 5. So the circles have to be the same color and the x's have to be the same color. But that means you need to have at least 3 beads of one color and 3 beads of another. But that's not possible because we only have 2 beads of each color. So again, this answer ends up being 0. And likewise, there's a counterclockwise rotation. That's r to the 4th. So far there aren't a whole lot of fixed points. Well, there's only one rotation left, the 180-degree rotation, or r cubed in this case. The fixed points there are those near necklaces where sigma of I plus 3 equals sigma of I. So that means sigma of 0 equals sigma of 3, sigma of 1 equals sigma of 4, and sigma of 2 equals sigma of 5. each one has an opposite that has the exact same color. Finally, we're in business. This is actually possible. Only now we're really forced. We know that the red, blue, and black colors each have to occur exactly once up here. Because then the opposite one occurs down here. And so there are 6 possible ways to choose that. You pick the red color bead in 1 of 3 ways, and the black bead in 1 of the 2 remaining ways. So it ends up being 6 fixed points. Finally, let's look at the reflections. There are 3 reflections of this type going through opposite pairs of vertices. They fix the vertex sets, and they send these 2 sets of vertices to their opposite. So we see the fixed points have to make these 2 vertices have the same color. These 2 vertices have the same color. So we see by the fact that we have exactly 6 beads in 3 sets of 2 colors each that these 2 vertices also end up having to be the same color. Because suppose these were red and these were blue, then these are forced to both be black. So again, we end up with 6 because there's 3 ways to pick one of these colors, then 2 ways to pick the remaining color to go on this one. Remember, there's 3 such reflections, so we're going to need to keep that in mind when we do the total count in a moment. Finally, there's 3 reflections going through an opposite pair of edges. And so those look like this. We'll call these S2s. And again, we have 6 fixed points. There's 3 ways to pick the color for this vertex, 2 more to pick the color for this vertex, and 1 here. And the reason why is because if you pick red here, you can't pick red here because red has to go there in order to be a fixed point. So now we can apply our Burnside's lemma and fill in the details. The order of the group is 112. One of the fixed points, group elements had 90 fixed points. One group element had 6 fixed points. So this was the identity element, this was R cubed. Then we had these 3 reflections that each had 6 fixed points, and then 3 more reflections that each had 6 fixed points. So we're looking at 112 times 90 plus a whole bunch of 6s. 6 times 1 plus 3 plus 3, so that's 7. If you're doing these calculations by hand, it's always easier to cancel as you go. The first factor is divisible by 3. The second factor is also divisible by 3. So now you've got much smaller numbers to deal with. So it's looking at 30 plus 14. That is 44, which is clearly divisible by 4. We get down to 11. So it turns out there are exactly 11 necklaces with 2 black beads, 2 red, and 2 blue. And here are the 11 necklaces, up to all the possible symmetry equivalence. These are the 11 equivalence classes, or more accurately, a representative from each of the 11 equivalence classes. So naturally generating them, well, it took a couple minutes, but it becomes non-trivial once you know exactly how many there are. And it's not too hard to see that the 11 I have are definitely not equivalent because, well, in some cases there's exactly 1 pair of opposite vertices of the same color. This one's the unique one where every pair of opposite vertices is the same color. So that's that equivalence class corresponding to R cubed. And then other ones, there's usually a unique one like this one, it's just the blue. So there's a unique color like that. And then if there's exactly two with a unique pair of opposite color vertices of the same color, there should be one other one like this. Where is it at? Oh yeah, right here. And one of them, the other two colors are right next to each other, and the other one, they're, when you draw the line of symmetry between the two blue colored vertices, they're symmetric across that line. And in this one, they're symmetric across the perpendicular line. And so you get these two options. And then you choose which color that is. So here I chose blue, but you know there's three other choices. So 2 times 3 is 6. So that actually gives 6 different necklaces on this list. Plus that one is 7. So there's 4 left. And they're found by starting with this one, where everything is adjacent, like that. Or starting with the unique adjacent pair and then alternating the other two. Gives you the 3 remaining necklaces. So there's all 11. Note that for the purposes of homework and exams, you're going to be asked to solve this counting problem. You're not going to be asked to actually list them, because that's not a group theory problem. That's a combinatorics problem.